Some listeners might remember that when we discussed the getting started example at the very start of this series, we noted that the axis would be offset to the segment center lines as shown here by these control points. As of now, our model does not actually display this particular property. Quite clearly, our axis within our geoDes model runs smack down the middle of the segments and along the segment center lines. Before we actually transfer this data to GeoCon, I would like to go back one more time to our cross-section definition and introduce that offset that I promised in the very first video. There are most certainly several ways of achieving this objective, but I would like to use this opportunity and introduce the concept of relative coordinates within our cross-section definition. This is the cross-section input dialog that we have gone through in one of the previous sessions, and these are the points that make up our cross-section shape. Let's bring up that cross-section shape to remind us of what this cross-section looked like when we defined it. We see that our origin corresponds with the control point B, 0, 0. I would like to introduce a new point in this definition, and I'm calling it 0 for reasons that we will understand very quickly. I'm giving it the coordinates 2 and minus 120 millimeters down. This point 0 will become our 0 point and our reference point for the definitions of the cross-section shape in the following. I've moved it 2 meters over to the side, and I've moved it down 120 millimeters to account for an asphalt cover that's usually placed on top of the concrete, and typically the top of the asphalt is the actual location of the axis and not the top of the concrete. So this point will move our cross-section over 2 meters and down 120 millimeters, as this will become our reference point for the cross-section shape. So we have introduced our reference point now, and we now need to communicate our intentions to geoDes. Please take note of this column here, and the header already gives it away. This is a place where we can define reference points. For example, if we put 0 here, then this would mean that point 1 will be computed, the coordinates of point 1 will be computed in reference to our 0 point. So 9 meters will be measured not from the origin of our cross-section coordinate system, but instead from the location of this 0 point. Let's have a look what it does. I'm accepting this input data, and I'm bringing up our cross-section again, and we can already see that this point here has moved out, as it references now to a point that's 2 meters offset. And I'm going to repeat this now for all the other points. I'm going to copy this entry, Ctrl C, and I'm going to paste it for the other points. Accept, and our cross-section has moved over by 2 meters and down by 120 millimeters. Our cross-section as a whole is now defined in relation to point 0 because we have referenced every single point within that cross section to our reference point. And in addition to that offset, I would like to introduce one more feature for this cross section. I would like to introduce a crossfall, and that's done quite simply by rotating the cross section about the reference point. This is the column to do it. We can introduce a rotation angle, and I'm going to do that not by simply entering the rotation angle. I will do so by introducing yet another concept. I would like to introduce a local parameter. Right click, it's the same procedure as every time we encounter a table like this, and insert a line. I'm calling my parameter CF for crossfall, and I'm giving it 10%. Resolve. The program has now recognized that value, and I can use it here in lieu of a number. Remember, every numerical input here can be replaced by parameters, and not only that, it can also include arithmetic operations, just as an aside. So let's see what this does to our cross section. We accept, and here we are. The cross section is now rotated about our reference point at an angle of 10%. Quite a drastic crossfall, but it shows better in the visualization what we have done. Let's calculate all the data again, and let's have a look at our bridge. Our bridge now has a crossfall. It slants inwardly, and it has the desired offset of 2 meters from the axis to our segment center lines, just like we set out to do, and as I described in the very first video. There are 2 concluding remarks that I would like to give. First of all, I would like to point out that the axis pierces our cross-section at the origin, and since we've shifted the cross-section over by a reference point and the axis still pierces the cross-section at the origin, this is why we have achieved this offset here. And secondly, as we note, the bridges folder now is displayed in red color, which means that we have an error message here. The reason is that the program knows that we are considering a precamber. The program also knows that we have changed the bridge, and it wants us to synchronize our precamber data before we can actually pass it on to anywhere. It's more like a warning. If we change the bridge, we must make sure that the precamber is still as we intend in order to avoid errors later on. Pressing sync removes the error message, and we can now continue.